Welcome to our workshop on Introduction to Computational Neuroscience. And we have another person. Here we go. We're short of half a dozen, and we have twice as many participants as TAs and lecturers. Okay. Oh, we have more. Okay.
Maybe so.
Okay. Come on in and sit. So here's the plan. The plan that I have, and I hope everybody is familiar with GitHub enough that they can download the Jupyter notebooks that we're running. If you want to follow along with the Jupyter notebooks, then you need to do the following. You have to go to GitHub/Neuroblox/JuliaCon 2025 WS, right? Up there. And then you just clone the repository and put it on your computer.
Yeah, but
I have to repeat that. By the way, drinking and eating is strictly forbidden in this room. I'm sorry to tell you this. We're told that, right?
he's not about to say no now, but
By the way, the same thing at our university. It's always the same thing. You're absolutely forbidden, and then everybody drinks and eats. Okay. So let me repeat this again. So if you want to follow along with our presentation and the notebooks and the running of the code, you go to github.com Neuroblox/JuliaCon 2025 WS workshop. Go and clone the repository on your computer. Then what you want to do is you want to go with a terminal, right? You want to take a terminal, go to that directory where your notebooks are, and then you want to start Julia there, and then you want to use these commands that are in the README. And so to explain to you what we need to do here is we're saying using package. I mean, maybe import package or using package should always work, right? And then there's two commands which loads the general registry. And usually you don't have to load the general registry, but because Neuroblox has its own registry, you have to actually add first the general registry and then the Neuroblox registry. But you just copy and paste these things, right? Then you activate the directory where you are, and then you say package instantiate, which will take the project.yml and then download all the packages that are mentioned in the project and then create essentially a pre-compiled versions of all the packages. So then once you run the notebooks, then you're set.
so this should be in everybody.
Yes, you first clone the repository, then you go to the repository, run these commands in Julia, and then you can actually just say using iJulia notebook parentheses, and then you will create essentially a web server with the Jupyter notebook server, and then you can run all the notebooks. And yeah, it typically, right, it's just that in the Jupyter notebook, the directory structure, you start from your root directory or something like this, but you have to then find the notebooks. Okay? So that's, you can do this while I'm giving sort of the introductory presentation. It will take a while to do the instantiate. It typically takes about 10 minutes or something like that. Or it depends on your laptop, right? But since you're in computational neuroscience, you probably have a good laptop. Okay, so now what I want to do is to just give a general introduction to Neuroblox, if I can find it. Yes. Okay. Okay, so here we go. Good. Okay. So The idea of Neuroblox is that we wanted to build computational models that are multi-scale. Um, because what we are interested in is actually to make models of diseases, right? Of psychiatric diseases, neurological diseases. And the problem is that the brain is a multi-scale organ. If you start at the bottom, you have ion channels. We will talk about this, like how essentially neurons work. You have ion channels, you have neurons, you have assemblies of neurons, you have brain regions, um, and all the interesting chemistry is actually happening at the bottom scale. So if you take a pill, right? If you take a medication, if you take a drug, they will act on the neuron scale. They will act on the synaptic scale. But what the effect is on the top scale, right? Behavior, right? Whether you're depressed or you're anxious or afraid. These are all things that are not clear what the connection is from a neuron to the upper scale, right? And then on the left side, you can see also the different measurements that we have. We have measurements on single neuron scale. We have measurements on um, patches of neurons. Then we have EEG, which is a very broad, like just electric fields on the skull. And then the one technique that can measure the whole brain of a human is fMRI, but it has millimeter um, resolution. So that means that a millimeter cube is several 100,000 neurons, actually probably more. I think I once calculated how many neurons. It's an enormous number of neurons, right? So what we wanted to do is we wanted to create a tool that can bridge these scales and then actually make predictions from the bottom scale to the top scale and vice versa, right? So make predictions on how a drug works, right? How a drug acts on the whole brain. Um, and this is just everyone. I want to go over this very quickly. The basic idea now, I think, in clinical neuroscience and general neuroscience is that pretty much all brain disorders, neurological brain disorders, are dysregulation of circuits. And this is illustrated here. So this is a glucose insulin regulation. Probably you know all about this. So when you eat a bagel or a cookie out there, right, your blood sugar goes up, then the insulin goes up, and then the insulin will remove the sugar um, from the bloodstream because we don't want to have too much sugar in it. And there's actually two dysregulation. There's diabetes 1 and diabetes 2. Diabetes 1 is that if you can make insulin, right? If you don't have insulin, it's very, very bad because you eat sugar and then your sugar level goes up. Or you can also fall below zero, like you would fall below, the standard level of glucose so that you faint. And so you have to constantly regulate insulin, right? You constantly have to inject insulin. Type 2 diabetes is insulin resistance, which means that insulin goes up, but the sugar is not removed, right? So these are two different ways of breaking the circuit. And what we're trying to say here is that it's very hard to just use correlations to figure out what's wrong. What you need to do is to do dynamics, right? You have to have a system where you know the dynamics of the system, then you can predict what kind of dysregulation we have in a circuit. And neuroscience right now is pretty much based on correlations rather than dynamics. And so we wanted to create a tool that can produce these dynamics to then address dysregulation of circuits. Um, so the other thing that we were thinking as a team is like, how do we build a system um, for simulating, neural activities, the brain? How can we create computational primitives, right? So in electronics, it's very simple, right? In electronics, you have, you know, resistors, capacitors, all these things, and you can build circuits, and you can even simulate these circuits really nicely, right? So what is the equivalent thing in the brain? And this is actually work by Rick Granger at Dartmouth, who's a collaborator of us. Um, he developed this model of a winner-takes-all circuit. So this is a basic circuit of neurons that essentially is equivalent to a digital circuit of the first neuron right? So you have 5 excitatory neurons, or 4 in this case, and they're all inhibited by an inhibitory neuron. And the first one that gets the biggest signals wins, and all the others lose, right? Because what happens is that the excitatory neuron talks to the inhibitory neuron, and then the inhibitory neuron inhibits all of them except for the one that wins, right? And so it's almost a digital, flip flop kind of circuit. Um, and you can actually see, so this is the simulation. And by the way, in the notebooks, we will actually run this winner takes all circuit and to build it. Um, And so the basic idea of Neuroblox is that it's hierarchical. So the blocks are essentially the computational primitives, could be neurons, could be winner takes all circuits. And then what you do is you take those and put them together into hierarchical structures and then build up essentially a whole circuit of a brain. And this is one example that we actually built, and it's, I think, about to be published in Nature Communications. This is a circuit of the cortical striatal circuit, which is responsible, where we model category learning. So this is based on experiments with monkeys, macaque, um, where they see essentially 2 different patterns, and it's noisy. It's not always the same pattern, but these are 2 categories. And what they do is essentially they have to learn the categories, and every time they guess right, then they get fruit juice. And if they guess wrong, they don't get anything. Um, and they slowly actually get better and better at learning these categories. And we modeled it essentially with Neuroblox, the whole circuit. And I just wanted to this. I'm going through this very quickly because there's a lot to explain. But I'm just showing you. This is the cortical striatal model. And we have simulations essentially of all the brain regions, all the interactions, and then actually there is you present a stimulus, and then you actually the model also gives the right or wrong choice. So the model actually comes up with a choice, and then you try it, and then if it's wrong, you get no reward, and if you get it right, you get reward, and that means that you're actually learning. So you're updating the weights in the cortical regions. And this is just to show you. Uh, and then we actually validated this at the macaque level, right? So we have local field potential measurements from the monkey model, and it actually agrees really nicely. And we even made predictions with the model, computational model, that were actually not in the data. And this is always a good sign. Like if you have a computational model, just to get the same result as the experiment is not enough. What you want to do is you want to use the model to have predictive power to show something that you didn't know before, because otherwise we're just repeating, right? We also have a GUI. I don't want to go into it too much because it's currently not running. I'm working on it, and I promise that I will have it posted by September 15th. Um, but actually, the GUI is based on Mercator projection map. It's actually not really, Alan. You always tell me that it's actually not true. But what we did is we took the brain, right? And it's, by the way, not our idea. So the problem with the brain is that it's 3-dimensional, right? And all the regions are in 3 dimensions. And if you have a GUI, it's a 2-dimensional, right? So how do you show a 3-dimensional brain in 2 dimensions without having to rotate and project and da da da? And so we came up with this idea. So it's hard to see. So, but this is the contrast is not very good here, but it's essentially a brain that is unfolded, and the subcortical regions are in the middle, and the cortical regions on the outside. Brainstem is at the bottom. It looks sort of like a jellyfish, or not a stingray, right? So it looks like, very much like a stingray, and we built a GUI around this, so you can essentially place. So this is no. I mean, if you want to actually come and look at my laptop, has better contrast here. But anyway, we also have a pharma module. So as I told you, we're interested in how pharmaceuticals, how drugs interact with the brain. So this models essentially all the different receptor dynamics that happen in the brain. Um, we have a metabolic module. This is actually, there's a lot of interest in how diet affects the brain. So there's a lot of effects in aging. There's a theory that as you age, your energy levels are going down, your ATP levels are going down, and this is something we really want to model, and we have a lot of research on this. So it makes sense to figure out how does metabolism affect the nervous system. So, for example, if you go from a glucose diet to a ketogenic diet, you probably all heard of ketogenic diet, like people who don't eat carbs, they only eat protein and fat. Um, if you go to a diet like this, you're actually changing the balance of GABA and glutamate, um, and so it can actually affect your brain when you change your diet. So this is all stuff that we're working on. Then we also have a neuromodulation module. Hermann is working on this. So we're working with a group at MGH, neurosurgeons, um, to see whether we can actually put an electrode into this artificial brain and stimulate.
So at the top right, the stingray.
Yes, exactly. So that's the stingray, right? Exactly. Okay. And this is the team. So the top six uh, gentlemen's and Leon. um, we founded Neuroblox. We actually also have a company, and these are all, I hope, most of the collaborators. So we have a pretty big group. We even had a graphic designer part of the group, and some web developers. Okay. Um, Let me quickly go over this because I mean I'm praying to the converted. We're at JuliaCon. Why use Julia? Um, we actually 3 years ago, um, my wife and I. Yes.
So the various tools in Strey are open source. I mean, available.
Say again.
What the various tools that I show?
Yeah. So yeah, maybe I'll address this. So Neuroblox.jl, which is the main repository with the software that you're going to use, um, is not open source, but it's open to academics. So all we say is you can use the software for free in academic and non-commercial context. As soon as you try to make money with it, you should contact us and get a license. Um, that's our model because we think um, if you want to use the software and interact with pharmaceutical industries and work with companies that develop drugs, they will not want to use an open source software, or they would just use it and not involve us. So that's our business.
The pursuit of patron and validation. That's
Exactly. Right. Um, so we decided that we want to do this. I think it's important for academics to have the software available because then you can check it that is correct. But we hold the rights to commercial applications through a EULA that we have hosted. I think this is actually best of both worlds. Very similar to Julia Hub, the business model. So they contribute to open source software. For example, Graph Dynamics is open source. We just did an implementation of simulation-based inference that is open source. So we open source everything that we can, but then we have a in-between license for Neuroblox. And I apologize to the open source, um, but I think open source makes sense in certain contexts and not in other contexts. Okay, so why Julia? Um, we decided 3 years ago when we started this project that we would use Julia, right? Because Julia has just this structure that we needed to for our project. It's very fast. It's a high-level language. It's almost as Julia walks like Python and runs like C. Um, but what was more important to us is the performance and accuracy solving ODE systems, right? I think it's differential equations.jl is probably the best package for solving ordinary differential equation systems. And by the way, delay differential equation, stochastic differential equation has just the best solvers and has the fastest solvers. Um, there's no doubt in my mind. The other reason why we chose Julia is because of auto differentiation. So any function in Julia that you write in Julia, pure Julia, is auto differentiable, right? Because of multiple dispatch, you can and that is the big advantage of what Alan would call its composability, right? You can define essentially auto differentiation. You can define functions. You bring them together, they work seamlessly most of the time. So what we're trying to do is to solve the inverse problem with optimization, right? So the idea is, let's say you have a model, you have data from neuroscience. You want to fit the parameters of your model to the data of the experiment, right? And that can only be done with taking derivatives. There's also Bayesian parameter estimation, a great package Turing.jl that does Monte Carlo sampling in the posterior space. It's also composable. We're using modeling toolkits. So every model that we build is actually built on symbolic equations. So every neuron you essentially write down as a symbolic equation. Every neural mass models you write down as a symbolic equation. And then we essentially use modeling toolkit or graph dynamics to then compile it into a simulatable code. And it's pretty fast. Hierarchical, so we can compose. We can take neurons. We can assemble essentially from neurons when it takes all circuits, and we can take when it takes all circuit, build a cortical region. And we have hierarchical namespaces, shared parameters, observables, custom connection rules. Then also performance. If you're interested in performance of Neuroblox, go to Mason Prater's talk on graph dynamics. He actually built a system. Our modeling toolkit was so slow that we actually built a new compiler for symbolics to make this faster. And it accelerates tremendously. And here I want to show you just the links to Neuroblox. So we have now a new website, actually, Neuroblox.ai.
I don't think it's up right.
It is up. I was told it was up.
I think it's down.
Oh, really? That's embarrassing. I wanted to actually show it.
So
It's up. Yes, it's a very, very professional website. This is for the commercial arm of our company. GitHub, Neuroblox.jl. We have actually we have a course, a tutorial of Neuroblox that is based on the IP course that we gave in January, which is also on OpenCourseWare at MIT. And this is the link to that. And then I have another link to the JuliaCon 2025 workshop. By the way, did you all download it? And did the instantiate work? Everybody's fine? Cool. Very nice. Okay. Okay. So now what I want to do is I want to go to another presentation. Yes. Okay. 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 So now let's talk about neuroscience. I'm not a neuroscientist. I'm a physicist by training. So we have neuroscientists here, so they can correct me. So in general, what we wanted to do is to cover like just neurons, neural masses, and sources, inputs, and spike trains, and other things. And we'll have a notebook later for that. So in general, the biology of neurons, we have about 10 to the 10 neurons in the brain, 10 to the 11 maybe. It's a lot of neurons. And if you think of it, it actually, to just give you the fundamental problem, right? So do you remember 10 years ago, there was the Blue Brain Project, right? There was €1 billion given to a research consortium in Europe um, to build an artificial brain. They said, like, essentially in 10 years, we can build, fully functioning brain. At the end of 10 years, they were able to simulate 300,000 neurons, right? 300,000 neurons. That was the what they could accomplish. Think about it. Even Moore's law or Moore's law squared or cubed, um, it will not be possible in our lifetimes or even in our children's lifetimes to simulate a whole brain, right? It's just not possible. So you have to find other ways of, simulating brain circuits. Um, but generally, neurons are, these are the these are the famous drawings by he's from S- Spain, or I think the neuroscientists should know, right? So these are very old drawings from around 1900. Um, these are from microscopy slides, and so they show essentially the structure of a neuron, right? And the structure of a neuron is typically you have the soma, you have the cell body, which is I think A, then the dendrites. Dendrites are where they make connection to other neurons. So typically there's about 10,000 connections to each neuron, at least in some parts of the brain. And then at the bottom, the axons that then connect to other neurons. Right? This is a highly connected system. Um, and yeah, so axons conduct the action potential to other neurons, and then dendrites get about 10,000 connections. Um, the action potential, so everything in neuroscience is essentially about potentials, right? So it's all about ions and potentials and ion currents. Um, so, and we will, by the way, have a notebook on action potentials on the Hodgkins-Huxley model. So Hodgkins and Huxley, they received a Nobel Prize for this work to explain essentially how a neuron would fire, right? Um, and it's based essentially on potassium, sodium, and chloride ions, the model. And we will talk about it a little bit how this works, and we're actually doing some simulations in the notebook. Synaptic transition. So when a neuron talks to another neuron, um, essentially there's a synapse. When that is activated, there are some vesicles that are opening, and a neurotransmitter is released and then accepted from the other side. And then potentially, if let's say thousands of neurons receive a signal, then the neuron itself will fire. Um, and there's specific dynamics associated with these synaptic interactions. Um, and we'll talk about this a little bit also in the notebooks. There's different neuron types. So here, for example, class 1 neuron types is if you inject current, the firing rate will increase, right? There's other neurons where there's a threshold, right, where it doesn't fire at all at a certain current, and then a certain current starts firing. Um, there is, in general, when you have these neuron models, you have different regions of stability, right? You have firing or not firing, or different firing, rapid firing, or potentially even bursting neurons. And so these are often described in these stability plots. Um, Neural mass models. So I told you already, we have 10 to the 11 neurons. We can mold them all. And this was actually mostly work by physicists. Physicists, condensed matter physicists, they always think in mean field models, right? So let's say take 1,000 neuron, 10,000 neuron, 100,000 neuron, and you're asking yourself, what is the average behavior of 10,000 neurons, right? Let's say you connect them all together, and you're asking, and it's very similar idea of the gas law, ideal gas law, right? So we have 10 to the 23 atoms. We have no idea what they're doing, right? They're running around, they're kicking each other. Can we describe on an average level what they do? right? And very similar, they developed essentially neuron mass model, which are essentially mean field models of neurons. So approximate behavior. And the other thing that they found is actually if you take a bunch of neurons, um, the sometimes under certain conditions they have synchronous behavior, which means that they essentially create a rhythm, right? So they would all fire together in a wave, and then also wax and wane in terms of the activity. And this is called asynchronous behavior. So rather than all firing independently and randomly, they would all, burst at the same time and then also stop bursting at the same time. And some people think that this is actually the reason for the rhythms in the brain, right? So we know from EEG, we know there's, beta rhythms and alpha rhythms and so on. So there are specific frequencies in the brain that interact with each other. And they probably come from this synchronous behavior. Um, so so there are many, many different mass models, neural mass models. Um, there's, for example, Wilson Cone is one of the oldest ones that essentially describe the excitatory to inhibitory balance. Janssen Rid is a model for pyramidal interneuron populations, and Laura Breakspear model is a detailed ion gradient. So they took essentially Hodgkin's-Huxley neurons and did a mean field model on them. But there is actually now something that is called next generation neural mass models. And this is actually quite exciting because this is for the first time, this is like only a few years back. Not Shannon Campbell, but there's another group, Montebrio. What they did is essentially they took neurons. I think they took quadratic integrating firing neurons, and Shannon Campbell used Izikevich neurons. And they built a proper mean field model. And proper, I mean that they took everything into account in terms of the interactions, essentially created a model that describes the probability distribution, the dynamic probability distribution evolution of an infinite number of neurons. And what they came up with is a model that fully describes what a simulation of neurons do. So you can see here on the right, you can see the blue is a simulation of, I think, 10,000 Izikevich neurons at a specific, parameter set of the neuron. And the next generation neural mass models describes exactly the average behavior, right? So now we have models that can connect neuron parameters, right? So specific neuron parameters to average behavior, which was not possible before. All of the other ones, the other models are essentially phenomenological, just differential equations. So now we have a strict way of going from neuron behavior to average behavior. And so the idea is then we can take the brain, parcel it up, and then start replacing parts of the brain with neural mass models, which makes it computationally much more feasible. Right? We can get many orders of magnitude reduction in terms of what we have to simulate. And then deep brain stimulation. This is a treatment currently pretty much exclusively used for Parkinson's disease. So what you're doing is you're stimulating some parts of the subcortical region, and you're reducing essentially the symptoms of tremor. So Parkinson's patients, they often have trouble finishing a word, right? They get stuck. Also, they have tremor. And it turns out that if you stimulate about 100 hertz in the subcortical regions, the SDN, then these tremors go away. But unfortunately, we don't really know how this works. So we are actually helping people to build models on how to better understand this treatment. But then there's also the other thing that it could be used for other things, right? It could be used. I mean, there's ideas of using it for depression, and I think anxiety. There's certain other ways of using it, but nobody knows where to put the electrode, right? And how it works. Um, so so we built stimulus blocks. So we have external inputs, right? So this is an example. Actually, Hermann built this. So this is a um, DBS protocol, right? So you can essentially create these pulse sequences. This is typically how it's used. It's used in pulse trains, right? So you give 10 pulses, then you have a pause, 10 pulses and a pause. It's a typical protocol. Um, and the other thing is you can also smooth them. The reason why you want to smooth them, first of all, in real biology, if you put an electric field in a brain, it will be shielded and it will be there's some capacitive effects. You will never get square waves into the brain anyway. But it's also better for ODEs, right? If you have a very sharp corner in an ODE, you have to worry about the derivative at this point, and you have to take care of that. So it's actually better to smooth these things. Um, and this is an example of the basal ganglia model with DBS. Okay, so now what I want to do is to switch to the notebooks, and I have a tab. So we wanted to do this is something we can run through quickly. So the first notebook that I want to do is JuliaCon Neuroscience WS. So this goes through the basic idea of neurons to be driven by electric fields, right? So this is um, the basis of all neuroscience, and we will go essentially through Hodgkins-Huxley equation. So the first thing that you have to understand, um, if you have a cell membrane is an incredible barrier to ions, right? It's the first thing. As a physicist, I learned it. So water has an epsilon of 80, right? Is it 80 or 60? 80, I think. Epsilon of 80. A lipid membrane has an epsilon of 2, which means that the energy of an ion is the proportion of the epsilon higher energy than in the membrane. So an ion will never, ever, ever go through the membrane, will never be in the membrane, right? Because it's avoided energetically, right? So it will never breach this. The only way that ions can go through a membrane is by ion channels, right? Or channels that leak, right? Ions. So that's the only way. And then the other thing that you have to understand is we are essentially in salt solutions, right? So you typically, sodium, we have 150 millimolar sodium in the cell. And if you have, let's say, a closed membrane and you have an ion concentration, one on one side and another concentration on the other side, this concentration gradient, actually the thermodynamics of that gradient will create a voltage, will create a potential difference between the inside and the outside. And that's called the Nernst potential. So the Nernst potential is essentially, so I can make this bigger, but I think it's big enough, right? It's essentially the logarithm of the outside concentration divided by the inside concentration, right? And that should already tell you that this is thermodynamics. It's not actually electrodynamics, it's thermodynamics. The differences between these two. And what is in there is essentially RT, thermodynamics, divided by ZF. Z is the charge. So calcium, for example, acts much stronger than sodium or potassium, right? And all I wanted to do in a notebook, let's actually run this. So what we want to do is to run this. Should have probably run this before, but it should go pretty quickly because everything is pre-compiled. Yeah, okay. So what we want to do is so I have a function that calculates the Nernst potential. And then what I wanted to do is to give you a sense of what these voltages are. So a typical ion concentration of inside versus outside of potassium is about 140 millimolar inside the cell and 5 millimolar outside. Sodium is 10 millimolar inside and 145. I said like 150 millimolar salt in general outside the cell, right? and chloride is a little bit different. And if you calculate the Nernst potential, you get about minus 90 millivolts from potassium, plus 71 because it's inverted, right? It's the same charge, but it's inverted. 71 millivolts, and chloride is minus 64. So typically a resting potential in a neuron is like minus 65, right? But also be aware, Nernst potential you can only use when you have one ion type. So it's much more difficult to calculate the voltage when you have many different ions involved. And I will not get into this. But what I wanted to do is to show you the Hodgkins-Huxley model. So the Hodgkins-Huxley model is a dynamic model now, right? So we have voltages, right, that come through things like Nernst potentials. But now what we want to do is we want to create, maybe I can actually zoom in a little bit, right, make it bigger, right? So this is the first equation that you have to kind of understand. When there is a current, right, then the voltage increase that comes from a current has to do with the capacitance, right? So the capacitance of the membrane times the change in voltage, which is the current, right, has to be equal to any external currents that come into the cell, and then minus the currents of sodium, minus the currents of potassium, and minus the currents of the leakage, right? These are just ions that go across. These are typically chloride ions. And then you can calculate the sodium current, the potassium current, and the leak current. And this is a model that essentially describes the voltage dependence of these sodium channels and potassium channels and leak channels. So GL is essentially the maximum conductance of these channels, right? So if a channel is completely open, right, that would be the G. And the M and the N is essentially a voltage-dependent probability that the channel is open, right? And it sounds very complicated, but that's what Hodgkins and Huxley came up with. And what we can do is essentially run these cells. These are the parameters, so typical membrane capacitance, conductances, and so forth. And then what we can do is we can create all the functions that we need from the model. And here I just displaying the. Am I running this? Yes, I'm running this. So this is the voltage dependence, the gating variables, right? So different channels have different opening probabilities, right, as a function of voltage. That's essentially part of the model. And then what I want to show you is the gating variable time constants that are also part of the model. And then what I'm going to do is to run the cells. You can also do this yourselves. When you put this all together and simulate the voltages, I'm actually using Modeling Toolkit. Then what you should see is that should make this a little smaller, that this is actually a spiking neuron now, right? And that's why Hodgkins-Huxley, received a Nobel Prize for their work, right? So you can see that a typical neuron firing is you have a very, very sharp spike, and then you have a refractory period where it goes below the resting potential.
Right on the way.
Oh, okay, yes. Yeah, over there. Okay. Right? And by the way, if you increase the input current, they will fire faster, right? This is actually something you can try. So when you take this model, have the notebook, just increase the input current a little bit, and then you see that it fires faster. And just for the fun of it, I created two more. So these are the gating variables in the dynamic model, right? So you can actually look at what is the probability of opening one of the channels relative to the other ones, right? And the next plot is the currents. And you can see actually what happens in the action potential is that the sodium and potassium currents are exactly opposite, right? So when one is going up, then the other one is going up, right? Um, so that's actually, I think this is the refractory period. This gives you a general sense of like what is involved in a neuron. Okay. Very bad pen.
Yeah, that book. So the rule of that path, I'm gonna arbit it.
Exactly. No, that's
Yeah.
that's yes.
Yeah, this one's way better.
Yeah. Most people put them back.
Yeah.
Make the world a better place. Every time you find a bad pen, throw it in the trash. Okay, so that's all. Are there any questions about this notebook? We just added it because we wanted to, just show the basic principles of that neuroscience is all about electric potentials and currents. Yep. So, um, so now we go. Yes.
What am I adding to make it paragraph?
Let's see. Actually, so in the neuron model, there should be a parameter. So okay. So the I external is a parameter that you would have to increase, right? I external is like 10, so just increase it to 20 and it should fire faster, right? And by the way, all currents are, the units are like microamps per centimeter squared of the cell. Okay. So now it's almost 10. How do you want to handle, breaks? Should we just go for, like, let's say 55 minutes, have 5-10 minute break, come back, have a coffee? Because now we were going to start, going into the details of Neuroblox.jl. Do you want to have a quick break, or do you want to keep going?
I think they're normally done at the halfway point.
Okay, we can do that too.
The other route will probably do that. It was like that last year.
Okay, then let's do that too. Like let's do one more notebook, one more presentation. Um, Mason, do you want to do the block connections?
Sure.
Okay, so we're switching presenters and okay. So Mason will so Mason actually was part of the architecture of how to build a good infrastructure of blocks and connections between blocks, right? And he will actually talk about is that Julia is a very nice language for doing exactly these kinds of things, and hit it.
Yeah.
Yeah.
Okay. Yeah. So we currently have kind of a couple ways of structuring things in Neuroblox, and I'm going to talk to you about kind of the default infrastructure that we normally use, and I'll be giving a talk tomorrow on kind of our next generation of how we talk about some of this architectural stuff and the direction we're going, but this is kind of the current state of things. So yeah, I'll be covering basically how we lay out all our types, how we kind of structure the objects that we're providing, and then how we actually wire up all these components to make models. Um, so basically we have a type tree of we have, I mean, we call the primitive types here, but basically bottommost components. So these are often just the objects that actually have differential equations describing them. So these can be an individual neuron. It can be one of these neural mass models that Helmut talked about. It could also be things like stimulus blocks. So representing, say, an electric field or a probe someone put in a brain that's trying to drive activity. Um, but then we also have these composite types, which are basically bags of pre-structured neurons. So we have a type for basically a cortical block, and has a graph in it of these winner-take-all circuits, and each winner-take-all circuit is comprised of neurons. So we have blocks composed of blocks and composed of blocks, and then we have some abstract types and stuff, and a somewhat messy multiple dispatch based type hierarchy for talking about connections between these things. So this is kind of what our type tree looks like. Um, so we have, yeah, I mean, we have these observer blocks, um, which are for collecting, like I believe these represent collecting like EEG data and stuff like this, or fMRI data. So basically, the observer block would be observing some cortical region. We have stimulus blocks for, say, inputting, yeah, images, stuff like this. Yeah, so more or less as discussed. And then in practice, this is what one of these block definitions might look like. So this is our Wilson-Cohen block. Um, and it's just a struct that's currently, at least, it's holding a modeling toolkit ODE system. So basically, when you define one of these blocks, it has a bunch of parameters that describe certain things about the cell you want, or the population you want to talk about. So I don't really know any of the details of what these parameters in particular mean for this model, but then you have your parameters, then you have states. So in this case, this is this E and the I. So excitatory and inhibitory population, so it's their average activity, and then these are the equations just governing those activities. And then this thing just stores this modeling toolkit ODE system. This is just a symbolic representation of these equations. And then what we can do is we can then compose these sorts of structures together, and then implement connector equations that describe how they interact with each other. So, okay, here's another example. It's a LIF neuron. Um, and then, so if you have Neuroblox loaded on your computer, then you can use the help function, like the question mark help function in the REPL, to get information on some of these. I hope we have doc strings for all of them. Okay, we have doc strings for some of them, with references as to where we got these parameters and stuff like that, and where we got the model. So the other kind of main component is the connections. So we have these connector types that we basically use multiple dispatch to describe what it means to connect, say, a LIF neuron to a QIF neuron or something like that, and describe what actual variables are being affected by what in the presynaptic block to the postsynaptic block. Yeah. Okay. So this is what one of these connectors look like. So essentially, or this is the structure of one of these connector objects. So it stores basically a weight parameter that just describes how strong that connection is. And these are the things that are typically being, like, when people talk about learning, they're talking about like strengthening or weakening various connections in the brain. So it influences how strongly one neuron is affecting another neuron. And then we have equations in the connector that describe what actual thing, like, so the weight is going to be a parameter, and then the equations are, how those different variables in the presynaptic and postsynaptic objects interact. We can have learning rules in there, which are basically equations describing how the connection should change under learning conditions, basically if it gets positive or negative feedback. And then connections can also have callbacks. So you can have connections that change some parameter if some condition is met. So like a classic example would be like at certain time steps, we have certain connections that turn themselves off. So they're on for a certain amount of time, say in a stimulus block. You want to play a movie into the cortex, and then eventually it turns off. And then the simulated macabre brain is sort of thinks about what it saw. Yeah, so these connection rules, they can kind of print them. We have pretty printing of the connection rules. We don't have pretty printing, unfortunately, of the blocks. So they've been semicoloned out, but the connection rules can show you, what objects they're connecting and what those equations are and what the weights are. So in this example, we have just two LAF neurons connected together in I guess this is their standard basic connection. So the connection rule basically says that the LIF2's junction variable, this variable kind of describes the sum of all the inputs into this thing, and that will affect the voltage of the LIF neuron. And this is going to be this complicated, ugly equation describing various variables from the presynaptic and postsynaptic neurons. And right, and then there's these. This is a callback that basically says that when there's a certain condition on this thing. I think this is when the presynaptic neuron fires. Then the postsynaptic neuron, it's some neurotransmitter population should be changed. Oh, okay, that's it, guys. Okay, you want me to go over the notebook? Okay. Where is it?
So here, tab block connections. And so you can change to the Jupyter Notebook block connections. And we could just run. Could actually make it bigger, right? Yeah, how legible is this? So this is essentially telling you, this notebook is giving you an example of how to make a new block, right? If you wanted to create your own custom block and then create essentially connectors for that new block.
How do we zoom in a bit more? Or can you zoom it in a bit more?
Sure. Okay, like this.
Sorry, I didn't actually look at this notebook. Okay.
All right.
Okay. Yeah, so this is just how you can play around with the interfaces in Neuroblox. So we basically load Neuroblox. It exports a bunch of functionality for these things, and then we load some differential equation solvers so we can actually solve the systems. This named macro here, this is the same as if I had just written LIF equals LIF neuron name equals LIF. It's just a convenience macro that does that, because every object in Neuroblox has to have a name associated with it so that the symbolic system can kind of track which LIF neuron you're talking about in the system. So okay, I guess this is yeah. Yeah, so okay, here we get basically we get the equations pre-printed out of this thing. So since they're symbolic, they'll just automatically print out the LaTeX representation. And then we can look at the connection rules. So here we create a integrate and fire neuron. It's a bit simpler than the LIF neuron, and we can look at the connection equations. So the connection equation for this junction is very simple. It's just that the integrate and fire neuron is taking in some weight times a conductance. So Okay, yeah. So this is just about how there's two different types of connection rules here. There's this basic connection and this PSP connection, um, and they can act differently. And then essentially the way that you create systems of blocks is you just create a graph. So in this case, a meta digraph, and you add your different neurons to the edges of this graph. So I'm creating a graph where that has two nodes, one LAF neuron and one IF neuron, and the connection's going from the LAF to the IF with a weight of 1. And then we generate a ODE system from this. And then this ODE system is then passed to an ODE problem. So this basically this is where we compile all the symbolic equations down into numeric equations and raw Julia code, and then we can run it through a solver. Is this finished running? Okay. Oh yeah. Okay. It doesn't print out the result. Yeah. So there's your solution. Probably some nonsense because it's just one neuron talking to another, but yeah. And then okay, so that's how you can kind of use pre-made blocks from the thing. You can also somewhat easily define your own blocks. So basically it just has to have a system and a namespace. Um I still don't understand the point of these namespace variables, but you could just leave it as nothing. And it's for the hierarchical. It's only really used for these hierarchical systems. But basically, you just define one of these structs and define variables. So in this case, he chose the initial voltage is 6.5, and this output equals true says that the voltage is an output. Like in this Izakevich neuron, the voltage is one of the outputs, and the JCN variable is an input. So then it's governed by these equations with these parameters here. And here he put an event so that when the voltage exceeds some threshold theta, then this U variable is incremented. It goes to U equals U plus D, and V is reset to this reset potential. So that's because unlike the Hodgkin-Huxley neurons, these Izakevich neurons can't dynamically reset their voltage after they spike. They would just continue exponentially increasing their voltage forever. So we have an event that basically says once it hits this threshold, then you just reset it back down. So it's kind of a non-dynamic way of writing a spiking neuron that can reset itself. Okay, so then once you define one of these objects, you can. Oh, yeah, I need to run that one. Okay. Once you define them, then you can create these things and add connection rules between them. We have this annoying warning I want to remove, and here's the connection equations between this LAF and IZH neuron. So this is just using this basic connection rule. You can also define your own custom connections by overloading this connection equations function. So basically you just define a source and a destination, and then usually you want to wait, and then whatever keyword argument parameters you might want for your specific connection type. And in this case, okay, yeah, right. So this is just this connection equations function doesn't support adding callbacks and stuff. This is just if you have a pure symbolic dynamic connection equation. And so in this case, he chose to have the weight times the conductance G times the difference between this voltage and this synaptic potential. And then you just return the equation. So so then once you do that overload, then so before we had this as our connection equations between the LAF and the IZH neuron, and then we add the overload and we get some new thing. So then we can create graphs of these things, create a little graph, add some edges between them, and we can solve it. And we can look at what our output looks like. So success, it solved it.
Well,
Oh.
say like, or you have an edge, it automatically put the blocks on the.
Yeah. So yeah, we've done some violence to the the metagraphs package. Normally you're supposed to, I think, add nodes and edges manually, and they're just integers. Harris added some overloads some type pirated overloads that say that if you have these pairs of neurons, then yeah, so this will become a node on the graph, and this will come or vertices on the graph, and then it adds a weighted edge between those two. So I don't know if maybe I can just add a so it's usually not very informative to look at these plot solutions, but you can just load the plots package and plot one of these solutions like this. So you just plot the solution and then this horrible abbreviation for indices, IDXs. So for instance, say we can say the IZH dot system dot v, and that should we didn't load. Okay. Okay, I don't. Yeah.
Applying a lot of
Okay. Okay. Yeah, do we have a nice thing for just plotting like individual variables in Mach-E? Okay. I haven't really used our Mach-E interface. I guess this is yet another connection equation. So this is from IZH to LIF. I forget if this is this. Okay. So we define an equation from LIF to IZH, but we can go the other way as well. Define a different rule for IZH to LIF. And then create a graph where we have IZH to LIF should solve. Yeah. Right. So here, this constant current showed up as a keyword argument in the connection equations. And when we added an edge between those two, we had to supply this keyword argument. So the constant current here is 20. So maybe as a little exercise, trying to find a connection equation from an LIF neuron to an IZH neuron. See if you can find equations that do something interesting, I guess. You can also define connection callbacks. So these are callbacks that will do something when some specific condition is met in the simulation. So this will do a discrete event. So basically what this means is that we're saying if we have a connection from our IZH neuron to our LIF neuron, we want a callback that checks at each time step if the voltage is greater than this threshold. And if so, we're going to increment the synaptic conductance G with this spike conductance variable, which is a keyword argument to the connection. So in this case, okay, it has a default of 1, so we didn't have to supply it here, but we could add say, spike. Add some big spike inductance and see how that changes our simulation. Yep. Okay, so okay, yeah. I think I'll stop there.
I'm sorry, Mason. I put him on the spot here because I just said you do it. Okay. So this was just to show you how flexible of a system we built. We wanted to build a system that where you have complete control over all the models that you can think of. We allow essentially, whatever neuron you want to build, whatever rules you want to build, we can put it into our graph. So the basic principle is every ODE system that we build it starts from a graph, right? The vertices are our blocks. By the way, the vertices can also be composite blocks, could be blocks of blocks of blocks of blocks, right? And then all you have to do is essentially define these blocks, put them on vertices, connect them with connection rules. And you can put any rule in the connection, right? You can put, callbacks in there. You can put equations in there. It's a very flexible system. But again, if you listen to, and this is why I actually put him on the spot. This is our old way of assembling it. We probably will keep this way, and it's very similar to the new way. We build a new graph dynamic systems that assembles these systems much faster. You can see if you take 100,000 neurons and connect them together, the compile time is actually longer than the execution time in this system. And that's why we needed a new way of creating actually ODE systems.
That's true for like 2 neurons. I think 100,000 neurons would be longer than the AEV average.
Okay, so 100,000 neurons would be so this is how teach you how to make your own blocks, right? And now what we want to do is to actually go directly to the neural mass notebook. And that actually will show you real simulations and outputs, right? And we build actually a Mackie extension in Neuroblox to make plotting easier, right? So you probably all know Plots has an extension for ODE, like differential equations.jl. So when you plot a solution of an ODE, then automatically Plots understands that this is a solution object and then plots it nicely. And so we did the same thing with Mackie. Mackie we chose because it is the slightly, I think, better plotting system. Yes. I mean, if you want to create, professionally looking graphs, then Mackie has more options. And can I say this publicly? Mackie Go. And so we built in this extension so that we can essentially plot again solutions of our kind of systems with Mackie, and I will show you some of the examples. So what we want to do again, we want to start the package, activate in the current directory, and then load Neuroblox and ordinary differential equations. And by the way, this comes back to this, like when you import Neuroblox, you will see a little disclaimer and EULA, and you can. Okay, so let's start with a simple Wilson-Cohen model, right? So Wilson-Cohen model is one of the earliest neural mass models. Essentially, what they assumed was that there was a population of excitatory neurons and then a population of inhibitory neurons, and they interact with each other, but it's the essentially average activity of the excitatory population versus the average activity of the inhibitory neurons, and it's a super simple neural mass model, and you can, for example, build oscillatory behavior with these models, and so So what you can do is, I'm not familiar with the system. So what you can do is you can just take a single Wilson cone block, which is an ODE system essentially, and then compile it, make an ODE problem. You're all familiar with differential equations.jl, I presume.
What is the presumption?
Yeah, I should not make. So who doesn't know differential equations.jl?
I know that every time I run it, I wait for an hour. Then I get
Yeah, because the package has gotten so big that, that it takes forever to. This is why have you seen this? They divided it up into different things. You can now import diffiq TSIP5, and then not all solvers are being imported. But the idea of differential equations.jl or diffiq is that what you do is you first create a system, right? So the system contains all these symbolic equations. Then you take the system and create an ODE problem. Now, so the basic flow is always you make a system of equations, you create essentially an ODE system, right? It's actually renamed now to system, but you create an ODE system, then you create a problem. As Mason actually said, the problem does the following. It takes the symbolic equation, turns them into actually functions, and then can be solved with an ODE solver, right? And so there's always these three steps. You create a system, you create a problem, and the problem always has the time span over which the simulation happens, and then you solve the problem using a solver, right? And this is an example of a Wilson-Cohen. It's a very boring model because all that happens is that the excitatory and inhibitory neurons just go to a base level, right, and stay there because of the interactions of excitatory and inhibitory. Because if you have them connected, right, the excitatories tell the inhibitory neurons to get more inhibitory, and then it essentially goes to a base level. So then what I'm going to show you here is our convenience functions that we created for. So if you have a solution, and the solution object of differential equation essentially is it's actually quite complicated. It has all the names of the variables. You can index the variables and so on. It's actually quite complicated to access every individual connection. If we have hierarchical systems and hierarchical names, it's even more complicated because it could be that I want a voltage of a neuron that is in the third winner-takes-all circuit of the 100th winner-takes-all circuit of my cortical region, right? But this is the problem with hierarchical systems. Then you have to walk the names through essentially where you want to be. And that's why we created a convenience function that is called state time series. So you give the system, you give the solution, and you give the name of the variable that you want to look for, right? And so what we essentially here is a very simple system. There's only E and there's only I, and it extracts just the E out of the solution object and then just plots E. We want to move on to neurons now. So we have quiff neurons. So maybe you know or you don't know. So the leaky integrating fire and quadratic integrate fire neurons, they are of a similar class. What they do is essentially they assume that the growth of the voltage is linear in a linear and quadratic in the quadratic equation. So one goes linear up and the other one goes quadratically up. And then when it reaches a maximum, when it reaches a threshold, then it resets. So this is the simplest way of describing neurons. And in our systems or in Neuroblox in general, I think in Julia, you solve this by callbacks, right? You have essentially a condition, the solver, when it solves the equation, it looks at the value of the solution and says, okay, if it's higher than a certain value, then reset, right? And then you just, in the ODE solver, it just takes the variable, subtracts something, and then continues solving it. Okay, and then, so what we can do is we can take the system, solve it. So this is just a quiff neuron with a certain input. And then we define several functions. So this is a raster plot. So raster plot are typically used in neuroscience where you look at a threshold. So a dot appears where this spike is. That's not my simulation, by the way. So you can see here in this case, there's a difference in firing. It's actually, I think it adapts to a certain frequency of firing, because I think the initial condition is not set. Then we can also plot a firing rate plot. So this is the plot of how fast it fires. So it looks essentially at the distances between the spikes, right? And then it calculates a rate of firing. That's sometimes very interesting to plot. And then we also we can extract the voltage time series. And so this would be the voltage time series of the quiff neuron. So one thing that I wanted to say about this, actually at the IAP, we got these questions. So if a quiff neuron has a threshold, right, why are the peaks different? The height of the peaks are different. That really has to do with the solvers, right? Because the solvers, the condition is if the voltage is higher than a certain point, then reset, and the voltage will reach a different, level. You could, in principle, make this work by just telling the solver to only reset at this point, but that adds a lot of computation because then you have to interpolate and you have to sort of adjust the step size to the point where you want to go. So most people they say, we don't worry about the height of the peaks as long as the threshold for spiking is a little lower. You can determine the spikes. But it's a good question. Like the students immediately came out like, what is going on? We also have stochastic differential equation solvers. So we have, for example, a fancy model of a Hodgkin's-Huxley neuron excitatory. And this is actually a special neuron, Hodgkin's-Huxley neuron, that is modeled by the SDN. And we added here a name. There was a specific researcher that defined this neuron, Adam. And this block, did I execute it already? Yes. Okay. So this is a one neuron, and then what we can do is we can actually, just to show you, we can create a power spectrum. So this is a part of the convenience functions that we created. So you can take any time series, right? Take the power spectrum and plot it nicely in, alpha, beta, gamma waves, right? So you always have a nice way of plotting the results. Okay, then let's talk about sources. As Mason said, we have blocks that contain differential equations, right? That are dynamic blocks. But what you also want to do is you want to interact with the world. For example, we will in a few minutes show you a bigger model where a cortical block gets an image, right, presented. That's a very complicated input source. But you can also just define something very simple as a constant input, right? So you can create a block. There's a constant input. And you can actually look at the connection rules of that constant input block. What we can do.
I'm just sort of curious because I'm trying to follow along on
Okay.
fucking Plasticity. I think people are actually following along by
Hold on.
Yeah, people are working here.
Could you maybe help Alan?
I think people are trying to and kind of give up.
But
Where's my app?
but did you come later?
I think I late. So.
Okay, so the issue is I gave very detailed instructions in the beginning, and you have to kind of follow this along, because Neuroblox only installs if you have the Neuroblox registry involved, and otherwise you can't get.
I may have missed the
And we can help you too, in maybe in the break if you want to.
for meeting. Wow.
Huh?
It was having errors.
Oh, I see. Errors compiling. That's weird. Okay.
Oh,
Yeah, this is why we try to start from a new project, right? And then instantiate everything, and then you have exactly the same thing as everybody else. You should not have problems unless you use a really old version of Julia.
so that might be. So
Maybe. But Mason can definitely help you. Okay? And so,
I just don't.
okay. So what we're doing here now is we essentially created a constant input, right? Of a current of 3. And then we connected this input to a Wilson-Cohen model, right, that we had defined earlier. And then we built the equation, and now, instead of having this solution, right, it now adds to the excitatory an extra input, an extra current, and instead the solution is oscillatory, but then also levels off at a yes.
Question about like the reaction.
Yeah.
You guys seen the equation that's like this?
Yeah. Okay, so the squiggly line is from symbolics. So in Julia, the difference between an equation and a symbolic equation is always the squiggly line. So when you have a symbolic package installed, any equation, I mean, it's very clear. So in a programming language in general, if you say A is equal B, that's an equation. That's an assignment. You assign the value of B to A. If you say A squiggly B, it means that A is a symbolic variable, which is equal to B is a symbolic variable. And it's a symbolic equation. It's not actually an assignment, right? And so the way we built the system is by symbolic equations. So the connection rule is a symbolic equation that then gets simplified when you build the system into a problem, right? And the reason why we did this is because to be more flexible, right? Because if you build it with equations, with functions, then it's much harder to be flexible about all the connections and to assemble the system properly. I don't know whether I made myself clear.
You send it like this input is like adding on to that three.
Yeah, so all the connection rule does is it adds that equation to the list of all the equations, and then it solves all the equations and tries to simplify the equations. So when you, for example, have one ODE system has a junction, right? One ODE has a junction, and then you define a junction is equal this input, this block connects to the junction, and this block connects to the junction, or this block connects to the junction, right? What the symbolic system will see, there's 2 junctions that have the same name, and it just replaces the right-hand side of the junction with the junction in the ODE system, right? So it eliminates all variables that are freely floating, that are eliminatable. I don't know, is this a word? It should be if it doesn't, right? So anything that can be eliminated is eliminated by the symbolic system, right?
Sir, that type of connection we are is more like ways. for the current lines here, pretty old as well as say, bem. Yeah.
So, so the thing is, since we're recording this, maybe if this is a longer discussion, then you may want to ask this to the microphone.
Oh yeah. So I was wondering about like the current connection, and I guess normally like an electrical circuit, I would think of like a connection being that kind of all the input currents have to equal all the output currents. Is that
In these systems, this is not exactly true. I mean, it's true, I think, on a single membrane, right? So that everything has to add up. But here, I don't think, because of the synaptic interactions, I don't think, because some of the current comes into the synapse, so the action potential comes into the synapse, then that affects the neuron. I don't think we have a balanced equation like what you see in an electric circuit. I know, there's these rules like that, all the currents have to be the same. I don't think in the neuroscience models this is true.
okay?
These neurons are like a little battery.
So I think you could maybe think of it as each neuron being like a little battery. So like they can generate current from. So I think if you accounted for how much current each neuron was actually generating from chemicals stored in it by like metabolizing those chemicals, it can generate current, and also taking in current, it can do some chemistry to absorb that and interact with ions in its environment. You would find that there's a balance there, but you're not going to see that balance just by looking at the interneuron connections, because each one is interacting with its local environment and dissipating current or absorbing current.
Yeah, I mean, batteries are good because it's also non-equilibrium, right? I mean, it's an energy dissipating system. There's ATP used up, so that's why I think battery is a good analogy.
Okay.
Okay, but we can discuss more. I mean, if there are more detailed questions, I think after this notebook we'll take a break, and then we can discuss individual questions. So another thing that we implemented is event-based spike sources. So sometimes what you want to just do is, like, you say, okay, one brain region has a connection where you have essentially a Poissonian train of spikes, right? We have this often in a DBS model, for example. We have the cortex projects to the SDN or the GPE a signal that is essentially a Poisson train of spikes. And what you can do is you can just essentially create this input. This is a block that essentially produces a Poisson spike train. So for this we use distributions. Distributions is a package in Julia that covers pretty much all probability distributions. So Poisson distribution, for example. And all we have to do is essentially create one of those spike trains. And then we can also come up with a custom spike train. So, for example, we can create a Bernoulli spike train, Bernoulli spikes, which essentially is which you define from the distributions.jl. You can then create a function to generate these spike times. So for each of these spike train generators, you essentially have to create a function that then actually creates and draws from these distributions. And then what we can do is we can create a connection that affects. So for example, if you connect a Bernoulli spikes to an IF neuron, how does the Bernoulli spikes affect the IF neuron? And you essentially write the equation again very simply. The you essentially just add the weight. Oh yeah, so every time it fires, it adds essentially a weight, an X-ray input, X-ray current input. And so we can try this out. So here now you see that the lift neuron, right, that would normally fire constantly, right, at a constant rate, right? Now it changes its rate as a function of time because there's a random input into the lift neuron, right? Sometimes there's an extra current, sometimes there's not an extra current. If there's an extra current, it fires faster than without the extra current. So you can essentially, with this procedure, you can inject randomness into your system with a very simple mechanism. Now we get to the deep brain stimulation. Again, Hermann coded all of this, and I hope everything is working. So this is essentially, we create a stimulus, which is a DBS. You create it at a certain frequency with a certain amplitude, with a certain pulse width. You can set the offset. You can also set the start time. So you want to maybe let the system equilibrate for a little while until you start the spikes. And you can also set the smoothness of the spikes. And there's actually, we created a convenience function to take that stimulus and extract the stimulus output. So that is essentially, so for 100 milliseconds, we have spike trains every, what did we say, frequency of 100 hertz. Amplitude is 100. The pulse width is 0.5, and this is the spike train that we get out of there. Okay. In this cell, what we do is we create another spike train, but this time we smooth it, right? So this is very sharp corners, right? These are actually exact sharp corners. And here we show the unsmoothed spike train, and here is the smooth spike train. And again, I explained to you, the reason why you do smoothing is because the ODE solver loves you if you do that. ODE solvers don't like edges and non-differentiable input functions. And then we also created and this is, by the way, the reason why we did this is because we worked with MGH, with the neurosurgeon at MGH that implants these DBS electrodes. And what he wanted to do is to essentially, in software, have the ability to set any parameters that he can set in his machine, right? So he has these Medtronic, pulse generators, and all the options that he has in on his device, we wanted to implement in code. So we essentially have a protocol DBS which sends bursts of spikes, right? And I can just show you how this looks like. So here we have a spike train of 3 spikes every, 400 milliseconds or something like this, or 450 milliseconds. So you have essentially a frequency of how many spike trains and how many spikes per spike train. And finally, what we want to do is to connect this DBS to some neurons, right? Like you're all looking for that. So here what we're doing is we are taking a Hodgkins-Huxley neuron excitatory block. We give it a little of an input current so that it would spike on its own, right? So, and then we connect essentially the DBS to this neuron, build a system of graph. Then another thing that is very important is in order to solve this ODE, and Hermann spent a lot of time on this, In order to solve an ODE where you connect a input source like a a pulse input source into an ODE solver, you have to tell the ODE solver when there are discontinuities. So whenever there is a kink in a very sharp turn in the input function, you want to tell the ODE solver, hey, at this point, be careful. Stop and think about what you're doing, right? And so what you're doing is
I would get the mesh.
um I think the problem is with adaptive ODE solvers, right? So if you think about it, so here's the trick. So the ODE solver is very happy with this flat region, right? So if the ODE is not very complicated, it's very flat. It predicts. It makes a big jump. It's just like, oh yeah, let's jump over to this point, right? It would miss the stimulus, right? The ODE solver is adaptive, right? They say like, okay, so if I don't have to make many steps, right, I can just jump over the whole thing. So that's why we give T-stops. Why we give essentially, watch out, something is happening here. Something, is going to change at this point.
I'm just trying to imagine that, like, I want to see the just what can you
I mean, but this is essentially what we're doing. So if you actually look at what we're doing here, is we're detecting these transitions. So Hermann built a function that looks at the stimulus and looks at the kinks, gets all the times, and then gives a list to the ODE solver to say, hey, all the corners, you have to solve it there. You can't just skip it.
I think there is a way for us to symbolically have these BBS circuits store in the ODE problem that they have T-stops associated with me. I think we just haven't figured out the right way to do that.
That makes more sense. It's a part of a different thing. But yeah.
Yes, and so this is the output. So this is, by the way, the last graph. So you can actually see that the Hodgkin's-Huxley neuron was firing along, right? It was just firing at a normal rate, and then when it got the DBS input, it just started like really firing, right? So it increased its frequency during the time of the DBS pulse, right? And if you build a system to model DBS, that's exactly what you want to do. You want to affect. Actually, this is oversimplification because actually the DBS is not affecting directly neurons, but it affects the synaptic interactions. So the real deal you will actually get at Hermann's talk on DBS in the mini symposium on neuroscience with Julia. Okay, and again, just want to remind you, if you want to go further, in this course, if you're interested in Neuroblox and you want to do something, we had put at the bottom of each of the notebooks, there are challenge problems. And in the IEP, when we taught this class, we would actually have 15 minutes of lectures, one notebook that the students would actually run by themselves and like learn along. And then they have like an hour and a half to do the challenge problems. So these are not necessarily easy challenge problems. There's sometimes it's open-ended, but they're a lot of fun if you're interested in how to use the tools and how to improve the tools. That's a good starting point. We also give some literature on how to do things. Okay, so we'll have a break. I would say let's have a break till 11, and then come back, and then we have, I think, one more bigger notebook that we're going to go through. Okay, and if you have any questions, also now is a good time to ask Hermann, Mason, and myself questions about whatever you have. Okay, thank you for sitting with us. Okay, so let's get started. I don't think I have a presentation for this because we already did all of the introductions. But what I want to do now is to look at hierarchical assemblies. So how to build things from other things and do composite assemblies. And what we want to do is essentially create a biomagnetic model of a cortical striatal microassembly. And then we actually, if we have time, we can go a little further on this. But essentially, what we're trying to do is create, and so I'm going to import Neuroblox. So the first thing that we want to build is what is called the cortical lateral inhibition circuit, or winner-takes-all circuit. So the basic structure is that you have several excitatory neurons and you have an inhibitory neuron. Inhibitory neuron just means essentially that if an inhibitory neuron fires, right, it will prevent the excitatory neuron from firing, right? So it's essentially a negative weight in the sense of block assemblies. The other thing is that typically inhibitory neurons have a different time scale, so they're much slower acting than excitatory neurons. But this is the circuit. The inhibitory neuron is connected to all the excitatory neurons, and the excitatory neurons are just open, not connected to anything yet. Right? We will soon connect them. And so what you can do is essentially you can build this as a graph, right? So what we do is we create a model name. So this is the namespace actually. Then the namespace that Mason doesn't like. And then we create essentially a neuron inhibitory block and an inhibitory block. And then we create an 5 excitatory neurons, right? And again, the convention is that when you create something in Neuroblox, by the way, this is the same thing if you create something in Modeling Toolkit, it has the same thing. There's a macro at named to make it simpler for you to create the systems by naming them automatically. The internal name is the same as the name of the variable. Okay? And then what you do is you create a meta-digraph. Meta-digraph is just essentially a graph structure that has direction. So you can create essentially vertices and you can create edges in either direction. That's why it's called a digraph. And then essentially what you do is you create all the connections, the vertices and the connections by just connecting all the excitatory neurons to the inhibitory neuron, right? And right, so the inhibitory neuron it goes to the excitatory neuron, and the excitatory neurons connect to the inhibitory neurons. So did I execute the cell? No, I didn't. Okay. So we built this graph, and then the command system from graph is taking this graph and turns it into an ODE system, right? So it assembles all the blocks, put it together, then looks at all the connections and adds the equation of the connections into one big ODE system, and then also simplifies it. Right? So it eliminates all the junction points, all the algebraic equations that are not necessary, like it eliminates. Then creates a problem, an ODE problem we are simulating over 1,000 milliseconds, and then solves it using a Vern 7 solver, which is essentially a Runge-Kutta 7th order solver. And so this is the result. What essentially happens is that exactly what we said, winner takes all, right? So the inhibitory neuron is firing, and one of the excitatory neurons are firing. They get inputs, and they only fire twice, right? And then gets inhibited. But the one winner that stays is the first excitatory neuron. Or actually, it's the other way around. Like I think the first excitatory neuron is over here. But you can see all of the excitatory neurons are competing, right? And one is going to win. And this is without inputs right now, but in a real system, all the excitatory neurons are then connected to other excitatory neurons, And so who wins depends on all the other inputs, right? So if one of the neurons get more inputs than the other ones, it will always win, right? And I think that's the basic understanding of, cortical regions, that they always have this balance of excitatory and inhibitory neurons. Yes.
Just wondering about that this is winner take all's only one neuron is based on the breadth. This set of parameters makes that be in your work.
I mean, in this case, it's sort of like the initial conditions. So I think actually the order of the of the states may matter in this case. But if you were to put random inputs, like let's say you were to add randomness to the inhibitor, then one would win, and it would every single run it would, and another one, a different one would win.
Are you considering the wiring topology there, but also be params? Or I'm mostly just wondering, like, okay, if there's a ton of simulation coming in to all excitatory neurons, is it still going to eventually settle to thanks. So just to kind of repeat, if in this simulation there was heavy stimulation of all excitatory neurons, is there something here that's actually enforcing winner take all to a single neuron, or is it possible that you'll get, say, two neurons win?
Oh, I see what you mean. Okay, so in a more complex system, it will change, right? I mean, because it's a dynamic system, right? So yes, the winner will not be the winner in all times, right? When then the excitatory neuron balance is changing, then somebody else will win. But it's essentially a filter. It's a pattern recognition filter, temporary. Like if you give a specific input, if you give a fixed input into the system, the network will end up with a certain firing pattern that is almost constant.
Okay. And there's I can ask about this later. It's more specific to the model. So
yeah,
thank you.
You had a question? Maybe. Okay. So this is our winner takes all circuit, right? And now what you can do is we can use stack plots. So here's a little exercise if you want to try this, right? I introduced stack plots, and I introduced raster plots, right? And you can apply all of these to these neurons. So let's see what we want to do. Now we want to connect two winner takes all circuits together. So we essentially create different currents to the different winner takes all circuits. Create essentially again a system. And now the interesting thing is we don't even have to create it from neurons, right? So in Neuroblox, what you can do is you can make composite blocks, which are blocks of blocks, right? So we built essentially this structure here is built into a block, and then you don't have to worry about it anymore, right? So then it's essentially encapsulated in a new block that you can then instantiate by just saying winner take all block, right? And all the inputs is how many excitatory neurons to one inhibitory neurons, and what is the background current that goes into the system. And then, yes, and the density keyword sets the connection probability from each excitatory neurons to each excitatory neurons of WTA. So the density is often something that you know, right? In a specific brain region, for example, that the connection probability, so every neuron connects to, let's say, 1,000 other neurons, right? If you know that, you can calculate the density, the probability of making a connection, and then you essentially connect randomly between these excitatory neurons. That's typically how we construct the circuits. So every time we create essentially the same circuit, it will be a different circuit. But it doesn't actually matter if you take 100 of those, right? If you assemble 100 of those, then the average behavior will be similar. Okay. So what we can do is now we can create another stack plot. And again, just to let you know, in this system, the red traces are the inhibitory neurons, and the blue are the excitatory neurons. And you can see that now two of the winner-takes-all circuits, one excitatory neurons wins over all the other ones in both circuits, right? And you can play around with the software. You can change we can actually, so this is an interesting thing. If we were to rerun this, maybe there's different, let's actually see if I run this again, whether the different ones are winning. Like you see, right? That's exactly your question. If I rerun this, I have different wirings, right? Then there's still only one excitatory neurons winning in the winner-takes-all circuit, but it's a different one because it depends on how many connections it got from other neurons. So maybe this got 3 connections and the other one only got 2 connections or 1 connection. So then we can create what we call a cortical superficial layer. So this is not the cortex, but it's something like the cortex. So we build essentially, let's say, 10 winner-takes-all circuits or 100 winner-takes-all circuits, put them together. So in this case, we are creating 10 winner-takes-all circuits, right? So here, as parameters, what we can do is we can take the maximal synaptic conductance of the excitatory neurons, the maximal synaptic conductance of the inhibitory neurons, the maximal synaptic conductance from the inhibitory synapses for feed-forwards interneurons, and the background current and the density. So the density is only 1/100th. So we're only connecting essentially a 1/100th of all possible connections, right? That you have to understand. So you can either say each neuron is connected to a average number of other neurons, or you can say there's a probability of 1% of all the possible connections, right? And you can convert these two. One is dependent on the size of the system, and one is not. And we, for some reason, chose that it's dependent on the size. Okay, and then we essentially assemble the system. So you can see that what we do is we now create essentially in a loop 10 winner-takes-all blocks, right? So this is a yes. So this is a list comprehension, right? Is it called list comprehension in Julia also, right? Or generator, right? Okay. So this is like a bracket essentially with a for loop, and then it creates essentially 10 blocks, right, individually, and they're all called differently. They're all called WTA $I, which is then 1, 2, 3, 4, 5, 6 to 10. Then we create an inhibitory neuron, and then the meta digraph essentially is then connecting all the winner-takes-all circuits together with a density is equal to 1%, right? So every single winner-takes-all circuit connects to every other winner-takes-all circuit with a 1% density. And then all we have to do is to simulate and create a stack plot. And by the way, stack plot in this case, if you think about it, 10 times 5 is 50 neurons. And so I think we cut off the stack plot at like 25, but you'll see. Typically, you just want to have a sample of, yes?
So this block generates, you'll see the behavior I was also pointing out. Okay, look, in a single winner-take-all session, you can actually have 2 neurons spiking at the same time.
Yeah. No, absolutely.
That's what I was asking.
Yeah, no, exactly. That's yes. So in this stack plot, so is this? 10.
Not AC. I know.
These are all 50 actually, right? So this is actually all 50. So again, what?
Two cases here that you have, but
Okay. But you see, like it gets pretty random. Like the firing. Some of them are always silent, but then there is sometimes a flipping between. Oh, I see. No, I don't see any events here where
It just has to do with the random number.
it just has to do with the random. I could run it again if you want to. Let's do it. It just takes long to compile. Another reason why we started graph dynamics because we built larger and larger systems, and then you asked us like building a system with 100,000 neurons, and then the compile time is the age of the universe. And so we had to figure out a better way of doing this, and graph dynamics is the solution. Yes, exactly. So that's a neuron, and actually there's several of those, right?
so would you call that multiple winners, or what would you call that? It's still winner. I mean, it's winners take all, which is still biologically though.
Yeah.
So I don't consider that though. Just find that interest.
Maybe we should rename winner takes all into we are all winners.
You were they would change the name to Elflick, right?
Oh. Okay. So now what we want to do is to actually so one of the things that always happens when you have a cortical layer, there is a beta input, right? So typically, as I said, there are rhythms in the brain, right? And so what we're doing is essentially we're using a next generation neural mass block as the rhythm of the cortical region, right? So when we actually do reinforcement learning or category learning, that rhythm sets the time scale of learning and not learning, right? So these are the signals of the circuit now, being plastic or not plastic. And so what we can do is we can connect essentially this neural mass model to a cortical block. So essentially, the ascending system goes in the cortical block. The cortical block consists of 10 winner-takes-all circuits with 5 excitatory neurons each at the same density. And what you can do is you can solve the system for 1,000 milliseconds. And what you should be seeing after it has compiled actually Mason had suggested that we would use graph dynamics.
You can. You're just in the system from graph.
Okay.
You can just turn it off.
And I think what you should be seeing, which I don't see, that there's a certain periodicity to the signal.
All spikes are synchronous.
Yeah, all the spikes are synchronous, right? Whereas here they're not. Yeah. Yes, that's true. Yeah. All the spikes are synchronous. Okay. And the other thing is that we introduced, which I haven't shown you yet, what you can do is you can also create the mean field. So often when you have measurements, right, let's say from a cortical region, all you have is the local field potential, right? You have an electrode stuck in a brain region, right? And you can then take time series of, and what typically happens is that this electrode will be the average, so the weighted average of the neurons around it, right? So you get essentially an average electric field from a brain region. And what people sometimes do is they say, okay, so this could be the average voltage of the neurons. if you want to get more complicated, it could also be described as the as the connectivity, right? The synaptic connectivity at for each neuron if you average those. But there are different models for LFP. But the general idea is that we can average over all the cell population and get an average voltage, average behavior. And here you can see that the driving frequency affects the firing, the average firing. You can see there's clearly a oscillatory behavior in here, and we can test this by taking the power spectrum. And you should see a peak at around 16 hertz, which is the frequency at which we drive the system. And you see, I think, harmonics of this frequency. So this log plot. Okay. And now what we want to do is we want to give it a stimulus, right? So we want to actually add some pictures to it. The way we did this is we don't really have a visual cortex like what would be in a human, but we essentially took a cortical region. We took as a visual cortex. The stimulus goes into the visual cortex, which is just a superficial cortical regions, and then we have a connection from one cortical region to another cortical region, which could be the prefrontal cortex. They're both driven by the same frequency, right? And then you give them stimulus inputs, right? And the idea is to slowly build up to a system where, let's say there's a stimulus, there's a pattern, right? And every single time the circuit properly identifies one pattern, we strengthen the connections that make the positive decision, right? So this is sort of like a learning rule. This is we are building up to this, and this is possible to this connection. Okay. So here I just want to build this for you. So we build now two cortical regions, both with 10 winner-takes-all circuits, and you can already anticipate that all the compile time will be longer. Then we're creating the ascending system by the next generation neural mass models. We then take the images. So this is an image example that actually we were using. We show the same dot patterns than in the macaque experiments. So these are images that are randomly have two categories, and actually we have the categories stored also. So we can tell whether the decision was correct or incorrect. And then we are creating the pixels. So this is one example. We reshape it to. I just want to show you how one of these images look like. So this is a pattern, right, that goes in, and these patterns just connect randomly to the neurons of the visual cortex, right? So they're projected essentially onto the visual cortex, and the visual cortex has to figure out itself what to do with this. So there's no pre-learning in the system. And then we assemble everything into a graph. And simulate it. And it will take a little while because it's like two cortical regions that talk to each other. And by the way, it's boring because we don't even plot it, right? So the challenge problem is to actually plot this. But it's pretty boring because we only show one picture, right, to this. let me actually then go to the presentation of the reinforcement learning, and Mason, you're going to assist me because he built a lot of the system, so he knows a little bit more, but I'm going to present it, and to show you how to build a more complicated system. Yes.
Hierarchical. So is the
What is the model? So can you take the microphone so that we all hear, that I don't have to repeat your question?
So there is this winner take all block,
Yeah.
and I was just looking it up in the documentation. It says okay, it's a winner take all block, but it doesn't say what is the model. Like there are several different models, different papers. I don't know. At the beginning, you showed some diagrams in the first presentation. I think
Right.
it was the paper by Lazzaro, one of the first proposals. So I was just asking her, on which paper is based the implementation of the winner take all block.
I can look it up for you. I don't know offhand, because we just implemented. Rick Granger is the person who is a big this is his favorite, basic computational primitive. And we were discussing, that there's quite a bit of evidence that they actually exist in the brain. But I can look up it's a pretty simple system. I mean, it's not very complicated.
Thank you.
So I can get back to you on this. I'm sorry. Okay. So let's switch back to the presentations. We're actually just on time, so we don't. Okay, so let's see. So this is synaptic plasticity. So this goes into that the connections between neurons can change, right, over time. And this is part of learning. So there are actually several timescales at which these happens. The plasticity can happen in milliseconds, but it can also happen on the minute timescale. There are several mechanisms for learning. There is a principle that was developed like in the 40s by Donald Hebb, which essentially says neurons that fire together wire together. So the more often a connection is being used, the stronger it gets. That's Hebbian learning. And we implement Hebbian learning to some extent but we apply Hebbian learning only when the decision is correct between the visual cortex and the prefrontal cortex. And it's based on so we build actually and I told you, I think it's about to be published. I think we have a bioarchive paper on the cortical striatal circuit built with Neuroblox. And it was essentially to simulate Earl Miller's data on the macaque. So he had like extensive data sets on macaque monkeys learning patterns. And he has essentially data from all different brain regions. And so we use that data to compare it to our model. So the idea is essentially that a monkey has electrodes implanted, and they look at the pictures, and then they get apple juice, I think, every single time they get it right. And they really love apple juice. Okay. And so this is the cortical striatal circuit model. It looks very complicated. So again, we have essentially the visual regions, we have a cortical region, and then we build essentially a system, the striatum. TANs are actually random number generators. There's a lot of discussion in the literature what they do, but we implemented them essentially as noise generators. And then there are different learning rules that apply. So here's the decision, right? Here's the monkeys look to the right or left to make a decision, right? And that feeds then back to the learning, updating the learning rules, the weights. And so we build a lot of these subcortical regions here with different neurotransmitters. And again, this is in bioRxiv, but should come out very soon in Nature Communications. The model pretty much replicates the reinforcement learning. There's one little thing in this model that we predicted, and we call this in the lab bad idea neurons. Apparently, there are neurons in the system that you can identify that know better, that if you listen to these neurons, you can make better decisions. And these are neurons that fire despite the fact that they know that they're wrong. So bad idea neurons make the system make the wrong decisions even though they know it's not correct. And we had a lot of discussions about this, right? Because, there is sometimes a reason for not making the right decisions, not to get juice, right? And so it's an inherent thing in biology that we want to be a little, unpredictable. So this was an interesting outcome that was not in the data, right? So we built a model around the data, and then these things came out, and then we, then it's really a predictive model. It's a model that gives you more than you put in, and that's, I think, should be always the goal of computational neuroscience.
And they found these neurons.
Yes, and then actually they interrogated the data more carefully, and then they found exactly the same behavior in the data, but nobody had actually looked at that. So that's, I think, a success story for this.
So in that situation, do you want to be something that bad idea in this case?
Something like that. I mean, you don't want to always follow the path of least resistance, right? You want to. Some people are more explorative than others. I think we would have never found, America would never have found if there was not people who did the thing that they shouldn't have done. Anyway, just one example. Okay. So in general, the model incorporates, there's something that probably experts will know: long-term potentiation and cortical synapses. So a lot of the learning is regulated by dopamine. So we model dopamine, not explicitly, but we could do better. So the way this works is essentially that every single time there is a correct decision, right, we essentially update the weights between the visual cortex and the anterior cortex. So that's what I was talking about, right? So the model essentially takes the data, right, filters it through the system. Then there's a decision made, essentially, between two choices. If the right decision is made, you update the weights between the visual cortex and the anterior cortex, right? And then you move to the next round, right? And then you do essentially learning cycles. And so, for example, here you can look the average synaptic weight increases as the functional trials go on, right? So initially you have weakly connected neurons, and then every trial weights are increased by a certain rate, and you see that you have an increase in average weight every single time you run this through. And then you also have plasticity in these connections here. So that essentially learns. So this is the dopamine interaction. So the decision is made between these two striatum blocks. Which one is stronger is essentially winning. And so these are the rules that are applied. You have cortical striatal synaptic plasticity. I think I will not go into the details of this. And to summarize, and we will run the notebook because we only have a few more minutes for running the notebook, and I want to run the notebook. So this is essentially describing the cortical striatal learning system that we built in Neuroblox. You can actually go to Neuroblox, right? Neuroblox.jl has the model built in. We have a simple model that runs in a few minutes. And then we have the full model that is in the paper, and that runs now in 4 hours, I think. If you turn on graph dynamics, you can run this in 4 hours. Otherwise, it will take 40 hours. So graph dynamics increases the speed by a factor of 10.
And the runtime is approximately the same,
But the compile time
is because of the remakes and stuff.
Yes, exactly. So you can actually try this yourself. So we are running, I think, 600 trials. So 600 times it repeats, and you can then get all the data out of this and analyze it yourself. Okay. And let's do the last thing that we wanted to do, and to run the where is, did I not open it?
What is this?
Oh, learning.
The model.
Say again?
When you say compilation time, that's the then have the model compiling and not like Julia.
It's the same, right? So there are two parts of it, right? So I mean, one thing that you have to understand in Julia is a just-in-time compiled language. So when I use the notebook, right? So I build something, right? Then it builds a structure. When I say ODE problem, it compiles that part of Julia that is needed to create the ODE problem and then executes it. That's why in Julia, often what happens is you run something once and it takes forever, and then you run it another time, and then it runs like in a few milliseconds. That has to do with the compilation. It wants to act like Python. It wants to act like something that is in a REPL, is interpreted, but it's actually compiled underneath. What we mean by compile time is when you build the graph of all the components that you have, to build the system from that graph, you have to take all the equations and put them together and then create functions from these things so that you can use an ODE solver to solve the system of equations. That is, as Mason said, n to the 4 in terms of neurons, right? N to the power of 4, if you have dense connections.
Because you have co-dense connections, you're going to have n squared expressions in this big collision body. And then the compiler wants to look at all the pairs of expressions. It's try-solve, so it's going through n to the 4.
Okay.
So if that's in the end, are you able to get that?
Oops. There's this magical thing where instead of writing out every single equation for every single plot, you just loop over the similar stuff.
Magic.
Well, Helmut told me because if you say you are 10 neurons to the same type, then it'll just write out the equations of the first neuron and second neuron, third neuron. And they'll just write out all the equations even though they're duplicate. And model exists, it doesn't really have wear on this. That was why we fell trapped in it.
Okay, so I'm going ahead and execute all these cells, right? And so what we're essentially building here is a system that can now learn, right? So the idea is that we create this cortical block, the visual cortical block, then the cortical block. We have a stimulus, again, like in the last example, we have a stimulus that is set. We have an ascending system that pulses, that gives the rhythm. And then we create a Hebbian plasticity rule. So it's a learning rule. And the learning rule is just a Hebbian rule, right? That essentially says that I increase the weight by a certain value, right? Relative to the activity at this junction. And you can essentially create a learning rule. You can add a learning rule to any of the edges, right? So here I create the learning rule for the connection of the visual cortex to the anterior cortex. And then the other thing is that we needed essentially is an agent. So the agent is sort of like a struct or I wouldn't say object because objects don't exist in Julia, but something like that, like a struct that then creates the classification. And then you have to create an environment, classification environment, and then you run the experiment. So for example, here, this is an adjacency matrix. So here is the connectivity between the different winner-take-all circuits. I think we don't show all of them, but you can see that that this is essentially the connectivity in with from with different winner-takes-all circuits, right? So you have winner-takes-all circuit 2, and these are connections winner-takes-all to 1 to 4, 2 to 3, 1 to 2, right? So this corner here. And you can see that after showing the image, right, there are more activity between winner-takes-all circuits, and then you increase the weights in this quadrant, right, between winner-takes-all circuits. So now what we can do is, and we have about 8 minutes. So what you can do here is, so we can essentially create a learning system, right? Where we now get the stimulus set, and we also actually getting, I think, the category of these learning sets. And so we downloaded and then we create essentially the striatum, the tans, and substantia nigra, right? And then we can also create a greedy policy. Mason, remind me, greedy policy is just if I get a reward, then I update, right?
Yeah.
So it's not like the marshmallow test, right? The marshmallow test is not the greedy policy. It's okay. And then what we essentially do is we're creating actually two learning rules, right? One is Hebbian plasticity, right? Hebbian plasticity is just essentially I'm updating weights according to how often things fire together, right? That's a simple rule that is always applied. But here what we do is we create a Hebbian rule that depends on a modulator, right? That depends on a brain region to tell, should I learn or should I not learn, right? So that's the rule that tells you if you want to get juice, you have to pick the right category, right? You pick the category that is represented by the image. And that's what the monkeys try to do, right? They try to figure out, is it category A or is it category B? And if they choose right, then they get an reward. Okay. And then essentially we create all the connections between these striatums. We create an agent. And I apologize, this may be a little bit maybe a little complicated. But what we want to do is to just show you that you can essentially create the results of our paper with this notebook. And if you want to go actually in more detail, you can just take the script that is on Neuroblox.jl under published models to run the full model yourself. And we actually had some challenge problems for the IP. You can take a look at this. So by the way, so what the agent does is this is like a typical reinforcement learning strategy, right? So you probably heard about this, right? So you have essentially a decision, you have an agent that applies an algorithm to the data, right? And then updates the weight according to the rule of the agent, right? So that's essentially we implemented the framework of category learning into the system. And you can see actually here, so now we're running trials actually, and the choice is 2, and it gets it correct, but then it gets it also, incorrect. And what will happen is that the system, as it learns, it will get better and better at picking the correct choice. So probably the trial that it got 5 correct was by chance, but now it tries, other categories. And you can see now it goes wrong a lot. So how many do we do actually? We're doing how many trials? I think it's defined further up here.
10.
Oh, we only no, we're doing more. It's 100. So we have 3 minutes. Come on. And then we run around the figure. We actually run 100. Wow. But I hope you can see that the chances are getting higher. So the interesting thing, I actually was surprised. So monkeys actually take a while until they learn, right? The problem with humans is that they learn so fast that it's actually very hard to model these experiments for humans. So what we do actually in experiments, what we do is we make them learn rules and then change the rules. Right. That's the only way that you can actually do this with humans. That we just confuse them. Then they take a while until they figure out that the rules has changed, and then they go and we just give them less CC juice. Yeah, but that doesn't really help, right? Because then they're not motivated. Motivation is very important for learning.
Yeah, so less motivation, slower learn.
Yes.
So
Do you want to take the microphone?
Yes.
And I'm not sure whether I'm the most qualified to answer these questions.
I think you already answered it. I maybe just wasn't really realizing what you were saying. But so the classification environment and together with the agent, when there's, for example, a successful response, like a correct response, it's kind of manually allowing the weights to change, or is it's not like it's not necessarily exactly how the brain would do it, right? Because the brain would just like, through whatever mechanisms are in the basal ganglia, it's, like dopamine mediated response, where just basically there's a signal that comes in that's like, ooh, this tastes sweet. So like, okay, that's going to cause the weights to go one way or the other. And in this case, it's a little bit more artificial, where we're just kind of directly manipulating the weights. But hypothetically, you can build a system that works just like the way the brain works.
Yeah, absolutely. That's actually, we're working on that. That's exactly, because dopamine is very important. And we modeled it sort of like the not super amount of cheating, but we simplified some of this. But you're absolutely right. And I think what's also important to understand is that if you want to use these circuits for disorders, then it's very important to get the drug interactions correctly.
Right.
And that's exactly what we're working on right now. So at this model, we didn't have the infrastructure to capture receptor dynamics. And so now we're adding all the receptor dynamics to the system. And we could essentially build the same system with a more realistic neurotransmitter dynamics.
You're talking about like STDP, or you're talking like a trisynaptic junction? I think I'm. Which receptor dynamics are you talking about?
I mean, for example, like dopamine
Mm-hmm.
is a neuromodulator. And if you actually look at oh, I don't have it. It's in my slides. If you look at all the interactions, there are many different neurotransmitters that are involved in the model. I can't really tell you all the details because I don't know. There's a group working on them that I talked to, but I don't know all the details.
Okay, I'll follow up after.
Yep.
Thank
you. Okay. So now we're just waiting. We're at 86 and we're 1 minute over. Maybe somebody else has a question in the meantime.
Do we have any visualization tools? Because now you explain it by, this is the framework, this is the codes.
Yeah.
Can you visualize the diagrams in a paper tool? Basically, how you debug this? How you understand that like the model that is running is actually the one that you want to run? Because like I saw the output, I run the same. I saw the output. It's like never ending. It's like this symbolics GL just dumping you all these equations. How do you know that it's the one that you want to run?
I'm not exactly sure whether I understand what you're asking.
Yeah, or visualize that. Okay, this is your blocks that is like winner takes all. This is how they are connected.
I mean, the general validation. So, I mean, you're saying that we may have made a mistake in putting
Yeah.
the system together. No, we have an extensive series of tests. Like we test on every level, on every dynamic of every level, whether they behave correctly.
I understand that, but like in this notebook,
Yeah.
you build a certain connections.
Right.
So, and then you train the weights for these connections and simplifying, but that's kind of it. But if I like mistakenly connect something in the wrong way,
Yes.
this will not learn or like will do weird things.
Yes.
Is there any way to understand what is the connections there, to visualize them?
Oh yeah. I mean, for example, when we look at the adjacency matrix, right? You can always go and diagnose anything where you look at all the weights that everything else is. Everything is connected to everything, right? So you can even pick subregions and look at these connections and how they change. But this is how you could diagnose, I think. Is this what you mean?
Yeah.
I think also in the GUI. I don't think we helped this yet, but the plan was to kind of warn people if they're connecting regions that are not traditionally connected, right? When like it will show you a wiring diagram with, okay, I connected, these two regions, and I think at least Rick was talking about how he would be very unhappy if people were allowed to innate, biologically unrealistic.
Yes, there's a lot of discussions in our groups of creating guardrails, essentially, right? So that you cannot just build whatever you want. But we know from the connectome, for example, that certain things are connected, certain things are not connected. Maybe you should not allow connections between brain regions that are actually biologically not connected. Is this what you were asking? I mean,
Yes. Yeah.
it's because I wasn't sure whether you meant that how would you find errors in the software of not connecting? But you're saying essentially, how do I diagnose when this thing doesn't work?
Yeah.
But that's like the scientific process. Like, I think the student who worked on this for like 2 years, and he probably did a lot of, unfortunately, this is how you build models. It takes a long time. And we're building these tools so that scientists can build these quicker, right? I mean, it's our own interest to be able to build models quicker and easier, so that you don't have to do a lot of debugging. But anyway, let's just finish this workshop by showing you the final graph, and it did fail. But that's not good. Okay. Sorry. Huh? Do I have to?
Are you? Yeah, you're updating your original that you're using. It created you all.
Oh, I
So
see.
just all pass it as the first part.
So I should do fig is equal figure? That's what you mean? Ah. Okay. I'm not sure whether this is so impressive. Anyway, I thank all of you for coming. I don't think we're perfect. But I just want to give you an impression about how Neuroblox does it, and stay in contact if you want to collaborate with us. If you're interested in using Neuroblox, we're here to help. It is available on Neuroblox.jl. I showed you the link. You can look at Neuroblox.ai and see what we're up to as a company. We will probably be hiring within a year. If you're interested in this direction, we have a startup, but we also have an academic arm, so we will probably do both. It's an exciting time, actually, for computational. And by the way, the other thing is, one thing that really helped us is that I think the FDA decided like 2 months ago that they want to essentially cut out animal trials for drug investigations. So they want to actually force people to do in silico models or cell models. But if you think about circuits, then the only way is to brain simulations. And that's a great opportunity for any effort to and I must say, I'm actually not so unhappy about eliminating animal trials. Even though we use animal experiments, I think the fewer animal experiments for medicine, the better. And if we can build good enough models and to replace, then we save a lot of animal lives. So again, let us know if you have any questions. Stay in contact. I think you have the contact. You can go to our website. There's also a website, LC Neuro, that you can contact us through. And you can always contact Stu. I mean, it's Helmut Strey. You can find me on the web. Okay? So thank you so much for participating. And thank you so much for the TAs and our runner. Have a good afternoon.